Okay, project for the day. I've got a new kit from Germany. This is actually part of a Kickstarter campaign that I contributed to, and since I gave a big enough donation to the campaign, I was one of those rewarded with a kit as a result of that. So this has come in at the basically almost on the last day of October 2019, and this thing is called the Nixielyzer, and it's I believe it's a 6-band monaural spectrum analyzer for audio frequencies that uses Nixie tubes as the display elements. It's very nicely packed. This is just padding. Empty box. So this is the Mr. Nixie site. There's actually a couple of sites calling themselves Mr. Nixie. I don't know if they're two different companies that happen to have the same name or just two different portals, but they definitely seem to have different content. The one that I'm looking at is Nixiekits.eu, and for those viewers of my channel, you might be interested in this. I'll just digress for a moment. I'm uploading my Train Odyssey 4 Part 2 Day 1 video as I'm doing this. So back to the subject at hand. Going to products, it's a small number of kits, but they all seem to be pretty good. There are audio kits. There's a phono preamp that uses a couple of vacuum tubes as the front end, and then the rest of it's integrated circuits after that. There's a power amplifier. I believe it's basically a headphone amp. It's very pretty, good styling. But they also have another one that's called a power amp. Somewhat different appearance to it. And then they have the Magic Eye VU meter. It uses a Magic Eye tube. That's really pretty. And this uses these magic kits or magic eye type of tubes. They're not, I don't know that they're strictly Nixie tubes, but it's sort of the Magic Eye technology. And it's also a 6-band VU, or not a VU meter, but a spectrum analyzer for audio frequencies. Very similar to the Nixielyzer, just a different type of display technology. And then the IN9 Nixielyzer, which is the one I've got here, it uses these Russian IN9 bar graph tubes, almost like pencil thin, and that's the one that was associated with the Kickstarter campaign. While here, I'll just show a couple of the other things they've got. They've got these various clocks. This one's called Lars, and Jenny Reloaded. The Numa Queen, or Numic Queen. The Strawberry Clock. The Anita Clock, which just shows all the digits of the time one at a time sequentially, and it's designed to kind of disappear into the background because it has minimal frame to it, and it's also a very large display. And the Nixie ornament, and RTF NTP to GPS receiver, which is apparently basically a GPS receiver for some of the products, the clock products that would be. And finally, another one which I've ordered, have not yet received. It was not part of the Kickstarter campaign that I was associated with. This is the Nixie Therm RGB. That'll be subject of another video. It uses a similar Russian bar graph Nixie tube, and I'll have a separate video on that once I get to it. But anyway, so the theme of this video is the IN9 Nixielyzer. So let's get back to that. The separate boxes include an option. This is a power supply. This is the US version. And this one here has no description. And that's because it basically just holds the Nixie tubes. So I'll put that aside for the moment. And then the aluminum enclosure, and I chose the silvery option instead of the black option. Put that aside. And then another one with no description, but this will be the components. All the components except for the Nixie tubes. So I think we'll get started with that. So the assembly and user's manual for the Nixielyzer is a 13-page document which is downloadable from the website as a PDF. It does not come printed with the kit. And you've got a friendly introductory paragraph there, some abbreviated safety instructions, location of parts inside the components box. Looks like the circuit board has to be broken into a couple of pieces along scribe lines. Talks about assembly of the two surface mount components before doing anything else, and then building up the main circuit board. It's fairly perfunctory instructions. It's not written for people who haven't built kits before or don't know their way around electronics. It's not like a Heath kit. More assembly, and then burn-in of the Nixie tubes. That's something that has to happen with these bar graph type Nixie tubes. If you don't do it, then they don't respond properly. And then enclosure assembly. There's a bill of material, a Stück list, and a circuit board diagram, and the electrical schematic. And let's get on towards assembly. Okay, I've got most of the parts out of the bag, everything except the case really, and the circuit boards. I'll just go through them. They're kind of scattered wherever they seem to fit best. It came with 6 of these, what I would consider cheapo IC sockets, and I've pulled out the nice screw machine type of gold-plated contact that I prefer to use for everything. Luckily I had enough in my parts bin, 2 different brands as you can see here, but they're equivalent. So I'll put these in the parts bin and put these in the kit. There are 6 soft rubber grommets to support the 6 Nixie tubes, rubber feet, 2 brackets, a kind of rubbery mounting bracket for the electret microphone, a piece of tubing that's used as a spacer, I think, for the microphone. It's supposed to be 8 of these longer screws according to the bill of material. There's only 6. I'm wondering if that's a typo. I'll find out. And then 2 smaller silver screws and 2 black screws, and 2 spacers that the black screws thread into. Then there's 2 555 timer ICs and 2 LM358 analog ICs. Those are amplifiers or op amps. And then these two chips here, the one with the tighter pin spacing, but it's still a dip, is the BA3830S spectrum analyzer IC. And then the little surface mount part is a NCY9100 compander IC. And then we've got 4 trim pots, slider types. There's only supposed to be 3 according to the bill of material, but there's 4. There's 2 small trim pots. Then there's 2 double RCA jacks and 2 1/8 inch or 3.5 millimeter tip ring sleeve or stereo phone jacks, and then a barrel connector for the power supply, power switch, and its aluminum looking button. Back here are some 10 nanofarad capacitors and 1 nanofarad capacitors. There's this little connector, male and female, that he's calling a micro match. That's for connecting 2 of the circuit boards together. And then there's a little surface mount inductor and the electret microphone and an assortment of electrolytic capacitors, a couple of small value ceramic disc capacitors, some more electrolytic capacitors, and then resistors and diodes in several different varieties. And there's one LED there. That's that little thing right in the middle of the picture that doesn't look a whole lot like an LED because it's a real tiny head on it. These here are 4004 diodes. They're just, you know, moderately high voltage general purpose silicon diodes. And then these here, let's see, 3 different values, or 3 Zener diodes, and then miscellaneous transistors and MOSFETs for various things, and then 2 bags of, I don't know what formulation those are, but they're fairly high value, 4.7 microfarads and 1 microfarad, even though they look like little you know, ceramic caps or something. They're they may be ceramic, but they're pretty high value for that. So that's the basic layout of all the parts. And then the remaining thing is the circuit board. And here are the 3 basic circuit board pieces. These guys here, I believe, have to be broken into 3 separate boards. And then you've got your main circuit board, which also has this section here, which is supposed to be broken off to make a separate board. And then this one here that isn't really a circuit board, but it's circuit board material, and that's a support for the Nixie tubes. Okay, time to break the boards. And then this one gets busted off here. And this part is waste. It's I think essentially almost the same as this one, but maybe for higher up on the tubes. And I think it's replaced with a plastic piece. So that gets put aside. I need to temporarily replace my larger chisel tip on my soldering iron with a smaller pointy fine tip. So this tiny little part here has to go here, and there are these larger pads at the corners, and the instructions are recommending putting just a pool of solder on one of those and then tacking down just that one point while holding the chip, and then once that's done, then the other ones can be sweat soldered. And I also am going to use this surface mount device, No Clean Tack Flux, just to improve the way the solder flows around those tiny little pads. And I've also got some very small, it's bigger than a human hair but not by much. It's a really small solder here. It's got a No Clean water washable flux in it, but it's 60-40. I've used that on other surface mount projects I've done. The trick is being able to see it with my bad vision. I have to use my magnifying lamp that I can't really photograph with this camera the way the eye sees it. Okay, well, I've got the corners tacked down. Now I just have to do the rest of them. I did inspect it with my jeweler's loupe to make sure there was nothing weird going on before I do this final soldering step. Okay, that one's on there. The instructions don't mention that the silk screen has the indication for a notch, which is what you don't usually see on these surface mount parts. And the IC actually has the dimple by pin 1. As near as I can tell by looking it up online, that is the correct orientation. I guess I'll find out if it's wrong. Now for the small surface mount inductor, which goes down there. I've already put my flux on it. So now those are down there. Alright, and then this one, even though it's not a surface mount part, the pins are a lot closer together, and just since I already had the small tip on, I soldered that one on. I'm not real keen on the way that this chip quick solder flows. Even though it's at the right temperature, it never flows as clean as the Kesters that I normally use, but I'm sure it's fine. So that's the supposedly hard part of this assembly, getting those things in there. The instructions actually mention using the extruded aluminum case as a circuit board holder, which isn't a bad idea, although I probably won't do it that way. I've got my own technique. So all those IC sockets are on now. The assembly instructions don't identify individual components such as resistors and capacitors and transistors and so on by their individual part number. It doesn't say install resistor 34 at this point. It just says, maybe you should start with the parts that have the lowest count, 590 k ohms, which is a single piece of that value. And you're saying, okay, where does that go on the board? So you can look at the bill of materials and see that a 500k resistor is R34, and then go looking at the board trying to find that. What they've done here is made a color-coded pictorial so I can easily find 590k, and I can see it's the only resistor that's a dark blue color, which hopefully will help me spot it on the circuit board. And there it is, complete with its resistor color code, which is a nice touch. It's right underneath the high voltage electrolytic capacitor there. Alright, all the axial lead resistors are in now. And then the three 4004 diodes and the Zehners. And the four 22K resistor networks. And the two little 220 picofarad caps and the two 1/8 inch stereo jacks. And quite a few of the small ceramic capacitors. And next up is this one LED which gets mounted on the solder side of the board and folded over flat like that. I'm not sure this is actually intended to light up in a meaningful way. It'll be inside the case. Its position in the schematic is in the ground lead of the 7808 voltage regulator. So I think it has a function due to its voltage drop rather than its function as an LED. And then 15 of the 1 microfarad ceramic capacitors, which are the ones I commented on earlier that don't look like they could be that big in capacitance and still be that small, but they are. And I tested them on my Heathkit digital LC bridge to make sure. And there's 15 parts, but or 15 parts used, but the bag had 3 spares. So if you're building one of these and have spares, don't freak out. And now for the 4.7 microfarad ceramic capacitors. This one's reading 4.3. And just for yucks, I'm going to try another one here. With all this junk on my workbench, it's hard to get the leads in there. That one's reading a little higher. These are obviously not precision parts. And then similarly, the 4.7 microfarad caps are all soldered on. Once again, there are 15 of them, and there is 1 spare included with my kit. And then all the transistors. And the 2 trim pots. And then the male micro match connector, which goes to the Nixie tube board. And the DC power input jack. There's a pink rubber tube that needs to be cut in half and slid laboriously over the curved legs of the power switch in order to leave enough to go into the circuit board. And there's the power switch on there with its aluminum knob stuck on. It is a click on, click off type. And the RCA jacks are on. Interestingly, this 100 microfarad 330 volt capacitor that's used in the high voltage section is intended for a photo flash application. So I presume that means the kind of thing that's charged up in a camera and then discharged suddenly to cause the flash to work. For this cap, even though the instructions don't mention it, I figure that metal plate on the end might be electrically live. I don't know if it is or isn't, but just in case, I guess I could have tested it out, but it still gives me the willies having it come right up next to this IC socket so close to the legs. So just for yucks, I put a piece of Mylar sheet that I had, cut it on there, put it on with a piece of tape as an insulator. And there's that big capacitor on there. An odd case is this polymer capacitor, which I probably won't be able to get focusing very well, but it's a 560 microfarad, I think 16 volt polymer cap, and these are marked differently from your normal electrolytic capacitors, which have a clear negative stripe on them, and then the positive lead is usually longer, so you can go by either one. Now this does have a short and a long lead, but it doesn't have the stripe. It does have this blue area, and some people might wonder, is that confirmation that's the negative side? Be nice if it just said negative, right? But this is pretty conventional for these polymer caps as far as I've been able to tell. And it's confusingly presented in the parts layout with the blue line on the bottom, which I think some people might interpret as putting that blue part in the other direction. However, even though the instructions don't address it at all, but luckily on page 5 of the manual is a color photo of the board showing the blue, well, that would stay out of the way, it'd be good, the blue part facing up, which confirms that it's a negative band and that the long lead is the positive. So that's something that could trick people up. I may mention that to Jurgen, the guy who produces this kit. And all of the electrolytic capacitors and that polymer capacitor are now on the board. The electret microphone gets put on next, and it does have a polarity. The circuit board is marked with letters B and R, and the instructions say to look for the small grounding tracks on a tiny little circuit board that's in there. Can't really see them with the naked eye. I had to use my jeweler's loop to look at it, and it says there's either 2 or 3 grounding tracks to the ground pin, which is the one that's marked B on the circuit board. So I've used my Sharpie to mark the B and the R on my microphone. And the electret microphone is now mounted and soldered. There's this little acrylic laser cut piece which slides onto a groove in the circuit board and sort of snaps on there, and that keeps the microphone properly supported and aligned for later insertion into the case. And finally, the voltage regulator IC with its heatsink, where the heatsink tab is pointing up. It doesn't have a heatsink bolted onto it. And one more thing on there is the 3 slider potentiometers along the front. Well, the included power adapter, assuming you bought the option with the kit, is a 15 volt regulated 2 amp switching power supply, universal input from 100 to 240 volts, 50 or 60 hertz. It has a German style plug, and if you bought it in the US, it comes with an adapter for US plugs. So very unwieldy. I think I'd almost recommend that instead of buying this power supply, you just buy a suitable power supply in your country of origin, as long as it has the appropriate barrel connector, which is probably a pretty standard size. They seem to have all more or less defaulted to that over the years. The first check is done with the power supply plugged in but no ICs installed, and turning the power switch on. It actually says switch the device on, have a first look at the LED on the button. I think it's supposed to be bottom. That's a bit of Germish there. So I'm going to push the power switch, And I do get the LED on the bottom. Turn the power switch off and the LED fades out. So that's verification of that. Now we're going to do a voltage measurement on the test points above the red connector. That's right about here. There's one for HV, one for ground, and one for VCC. So I'll get my voltmeter set up for DC volts. And it says VCC should be around 10 volts and HV about 13 volts at the moment. Well, I can't do that with my hands tied up, so I'm going to put the camera there, turn the power switch on, and probe and the power is 9.88 volts, so roughly the 10 volts expected and required. And then going to the HV, I'm getting 13.85, so that's also in the ballpark as expected and required. And now all the ICs are plugged into their sockets. 3 op amps and another op amp and 2 555 timers. Of course, each of these op amp chips is really a dual op amp. And with the power reapplied and all the ICs in, I'm once again checking the regulated 10 volt supply, 9.88, just like it should be. And now I should be getting on the high voltage supply roughly 140 volts. And I do. Now I'm supposed to adjust this trim pot until I get um, 140 volts. It's possible to buy this kit for use with argon tubes instead of neon tubes, so it can be adjusted. But I'm using the neon tubes, so I need to crank this guy in. There we go. 140 volts. That seems to be working. So now I just switch her off. And it takes about a minute before it's safe to handle, because this capacitor will be charged up until it trickles off. But that indicates that the power supply circuit's working and the high voltage oscillator and regulator circuits are working. It's all a good sign. Okay, now it's time to put together the Nixie tube board. It's a long, skinny, double-sided board. And there are these tube support grommets, some metal brackets, some screws. So we'll get started on that. And there's also this other support board here. And this is the one that gets the black tube support grommets, which are smaller on one side than the other. And helpfully the white rings, which get occluded by the grommets when assembled, are also showing the smaller diameter and the larger diameter, which helps with assembly. And there's with the grommets installed. And then the 2 black screws and the spacers get put on. Nothing really threads into these, there's just a tight enough clearance that the screws don't fall out. And then the female micro match right angle connector. See if I can get a good picture of it. There we go. It's a right angle connector. gets soldered onto the so-called tube soldering board. And then the two right angle brackets are screwed on. It's just a machine screw that self-threads into a tight hole in the fiberglass circuit board. There is no nut on the back of it. And then the formerly inserted black screws with their spacers go into the threaded holes in the metal brackets, thereby joining the two boards together. And here are the 6 Nixie tubes, IN9 Nixie tubes. These are marked with the old CCCP here, even though the camera doesn't want to focus on it very well. These are probably, I think, early 1980s. They're about Soviet manufacture, and you can kind of maybe make out there. Let's see. It's a Cyrillic IN9 there, but it is really hard to make out with the glare and everything. And all the Nixie tubes are taken out of their protective foam bag and inserted into the rubber grommets from the top. The leads usually are all tangled up and need to be straightened out quite a bit. And then the tubes are fed through from this direction. They actually butt up against the crimped part of the tube. The glass envelope butts up against the tube connection board or tube soldering board, whatever we're calling it. The solder tube. Yeah. And it's interesting to note that where the tubes are crimped, one lead comes out more or less in the middle, and the other one comes off to the side, and the pads on the circuit board are similarly offset, so that they line up pretty well. Obviously there's going to be another circuit board, probably this one, or maybe something else, that supports the tops of the tubes later on. Looks like I need to do some soldering now. Now I've got all the Nixie tube leads bent up, not quite straight up, but at 10 or so degrees from vertical. And I bend a typical lead up, I don't know, roughly halfway up to the edge of the board that I'm holding in my fingers, and then see if I can slip something in between there so it's easier to see. Like that. So up, down, and then up again. And the circuit board is built with a slot in it, and then it's metallized at the right edge. So there's the lead bent up and down and back up. The bottom loop is down in the slot, and just where it comes back up is where it's soldered and cut off. And here are all of the looped wires. Then I adjust all the tubes in and out of their grommets so that the white bands along the top here, these are the well, they're actually part of the insulator, I think, but they're also used for alignment, and those are all lined up now. And that ends up with maybe a millimeter or so of clearance between the bottom of the glass tube and the wiring circuit board here. And now it's time to plug in the two circuit boards with that small micro mesh connector, and it has to squeeze in there. A lot of pretty close tolerances in there. Okay, the first test. All the sliders are down. I'm going to turn power on. There was a little indication out of the tubes there briefly. Let me turn the light off, and then this is the volume level for the microphone. It says to turn it to maximum, and then talk into the microphone, and it should respond, although it says there will be the least response from the left hand one because most voices don't have that much of a low frequency component. But it's clearly working on all channels. It's a good sign. Okay, so the next thing to do is to turn the microphone slider all the way down so there should be no response, and set this one here. This is to roughly the middle position. That's the balance control. And turn the line level control all the way up. And I've got my music player here with some Amazon Music Library copyright free material. And I picked some organ music. So let's see how that works. Mess with the slider control here a bit. That's only one channel. That's the other channel. It's roughly balanced. way it's become clear why the leads on the back of the switch are insulated with that pink insulation material. You can see the leftmost Nixie's wires are jammed right up against the back of the switch there. Up next is the Nixie tube burn-in procedure, and it says I have to turn this trimmer fully clockwise. This is the one that was used to adjust the high voltage earlier. This is the one that needs to be adjusted fully clockwise. Then I have to locate the pads for X1, Y1, and so on. Those are these guys down here with the big holes. Short circuiting the pads with a pair of wire or a set of these spring tweezers, and I can do 3 of them at a time. So I've got 3 of the spring tweezers, and they just get stuck on kind of like that. What that trimmer does is it works with this IC here. This is one of the 555 timer ICs running as an astable multi-vibrator, and this pot adjusts the duty cycle of the square wave coming out of it, which in turn controls the entire power circuit that's common to all the Nixie tubes, turning it on and off rapidly somewhere between 80 and 100 Hertz. That's considered to be the blanking time when it's turned off. And that's useful for keeping these tubes from doing something they're known to do sometimes, which is instead of starting the bar graph at the bottom, it'll try starting at the middle and going up from there and leaving the bottom unilluminated. And so you can adjust the duty cycle there for better results in that regard. Now my tubes don't seem to be doing that, but setting the pot to full clockwise changes it to maximum duty cycle, so it's running the tubes as much as possible given the circuit. And now I have to start short-circuiting these guys, and these are all low voltage pads there, so I don't need to turn the power off when doing it. And it says start by shorting the X1, Y1 and watch the left hand tubes glow rising. The goal is to try to get the tubes to light up all the way up to the top of this darkened part of the anode mesh, which you can see here where it goes from kind of a black to a silver. So we want the tubes to light up there, and it can take up to about 15 minutes according to this. So I'm going to start by shorting out the first ones here. Well, come on. There. So now it's driving it up to that level. Okay, I've got the left 3 tweezers installed, and you can see the left 3 Nixies are all no longer responsive to my microphone input, and they're higher than they would have been, so I have to wait now for up to 15 minutes to see if I can get them all the way up to the top. It may be necessary to increase the high voltage a little bit if they don't go all the way up. So it does seem like they've gotten higher already in just the first few minutes. Especially this one here is getting close to being high enough already. So we'll come back and check that in a few more minutes. Okay, after about 10 minutes, they've all reached that same point. So now it's time to do it to the other ones. I'm supposed to let it cool off a little bit before I do the other three. Okay, we're doing the right three now, and the left ones are responding to my voice. The right-hand most one looks like it's already at its maximum. We have to wait for these other two guys to get up there, but the other ones on the left seem to do it pretty well, so I've started my watch here. Give it 15 minutes. Well, it only took about 10 minutes to get up to the full level, so that's good. Testing 1, 2, 3, 4. I have to bring the voltage down now because I raised it slightly for testing. Alright, I'm going to try my test music track again. Oops. I'm going to turn my speaker on. Well, that seems to be all working. Alright, I've got all the parts for the case out here now. There's this gold colored panel that describes the different frequency ranges. And there is the rear panel, the front panel, this one here, don't know where that goes yet, haven't read the instructions that far, and a couple black bezel rings, and then this clear acrylic piece. The 4 clear rubber bumpers are on the bottom of the case. Alright, these are the 4 screws that I bought at the hardware store. They're M3 x 10 screws, just like the ones included with the kit, except these have Phillips heads instead of the Torx heads. So I'm going to put this on the rear side of the panel to make sure that the uglier Phillips heads don't show. The ones at the Torx will be in the front. Well, the problem I ran into here is that even though these are the requisite size, M3 x 10, they must be just ever so slightly smaller in the outer thread diameter because they practically fall into the holes in here. I can push them in with some effort, grant you, but they barely grab the walls. They're not really making taps when they go through, or they're not cutting threads into the frame when they go through. So I'm thinking that it may be desirable to run back to the hardware store and find another screw of similar dimensions, perhaps a little bit wider. It probably won't be metric, that I can put in here in place of these. That's annoying. Well, it turned out that the Hillman M3 x 10 bolts, and actually all the M3s, are just undersized. The outer thread diameter is too small for what it should be, and that isn't going to work with these extrusions. They just barely touch the outer diameter of the hole, so they have very little grip and they would strip out instantly. So I switched up to a 540, and I think that'll go in all right. Now the trick here is that those black spacers that I showed earlier are supposed to go on and be screwed in with the screws at the corner, and then the adhesive backed front and rear panels are supposed to stick onto those bezels, and the heads of the screws pass through them without, you know, with as little clearance as possible. But I'm finding these are really tight on there, and I think that's maybe a little bit too much, so I'm going to turn them down in my lathe ever so slightly for a slightly easier fit. This is my poor man's lathe. I do have a proper lathe, but I'm looking for something that takes less time to set up. So I've got my belt sander here, and I'm just going to rotate this up against the belt sander until it takes off enough of the head diameter. Okay, I've got the rear bezel on using the 540 screws with the heads turned down ever so slightly. Now I got to clean my fingerprints and grease off of the bezel so I can stick the rear panel on over it. So here's the rear panel, and here's the protective covering for the adhesive back. And now when these screws, which are somewhat buried in the rear panel, are removed, then the panel with the bezel will come out as one piece. Next up are the two pieces that are broken off of the circuit board earlier, and this is considered top whiteboard 1, and the one with the notches is top whiteboard 2. The instructions say to pick up top whiteboard 2 and slide it with the cutouts facing to front into the uppermost groove of the aluminum frame. Kind of like this, I think. Alright. And then the electronics slide in. The alignment circuit board for the Nixies goes into the top slot there, and the main board goes into the second slot from the bottom there. Look how close that clearance is. Those electrolytics are right up against the ribs. This is a pretty tightly packed arrangement. Okay, it goes in like that, and the notches for the brackets fit into the notches in the top whiteboard too. Now I'll slide in the top whiteboard 1. Make sure there's no difference between one side and the other. Come on, get in there. Alright. And here I'm peeling the protective film off the other acrylic bezel. They call it a frame, and that's really a better name. A bezel is usually on the outside of something, whereas this is internal, so I'll call it a frame. Okay, now I'm using the M3x10 with the T10 Torx head on it, and these are also turned down in my quick and dirty lathe, and those are going to be used to secure the front frame to the front, or the front acrylic frame to the front of the aluminum extruded frame. Well, I ran into a problem with that. I still have this little microphone alignment tool in there. I thought that would be part of the case. I don't think it actually told me in the instructions to remove it, so I'm going to have to take that out because it's causing the acrylic frame to bow out a lot. Okay, now the front black frame is mounted to the extruded frame, and I just have to put on the front panel once I remove its adhesive backing paper. Okay, and now that's on. Alright, now there's the so-called silvery top frame, which has a protective film on the silvery side, and then the 3M marked adhesive backing paper on the other side. And that's going to have to be glued onto the top, and it'll adjoin the two white boards and this board. And that's the way that ends up looking. It's coming together. And now there's this golden colored audio spectrum plate. I have to make sure the side with the 63 goes on the left when viewed from the front. And once again, it has a adhesive backing protective sheet. And that's the way that looks. And then this clear acrylic alignment frame goes onto the top. It's got the holes in there, and then it's opened at the top so it's a little springy and just clamps on by friction. I found putting this on that it pushed some of the tubes down slightly in the grommets, so they were no longer vertically aligned. So I pulled them back up until the white insulator inside aligns with the plastic piece. And this is how the rear panel looks when it's installed. High voltage, do not open while operational. No servicing parts inside. Okay, now for the post-assembly test. Push the power button on. I'm going to bring the line output down and the mic level in so it's responding to my voice. I'll turn the mic level off, turn the line level on, make sure it's roughly centered left to right, and play my audio source. Seems to be working just fine. Alright, I've got the Nixielyzer positioned in my studio, and we're going to play a little music through it.
Almost like being in love.
So now, as usual with these kit videos, I'm going to go over the schematic and explore how the circuit works. You might assume this is based on a microcomputer, little microcontroller, an Arduino, or a PIC processor or something like that, but it's all analog. This is the schematic from the manual, and while it's a good schematic overall, it does have a characteristic that I'm not too fond of, and that is it's not laid out for easy comprehension of the circuit. It's like wherever things fit is where they go. And it also uses the Euro style schematic symbols, which are okay, but I've always felt that it's better to have a distinctive symbol for each thing rather than use rectangles for lots of stuff. And this one's not too bad. At least the only things that are rectangles are resistors. But still, I'd rather have a resistor look like a resistance element instead of a rectangle. So anyway, I redrew this in a larger format. Right here. I have it divvied up into sections. This is the line inputs, buffer and filter section, red and white, which would be right and left, although it doesn't really matter because it all gets mixed down to mono here. And there's both RCAs and it's feed through, so one of these can be the input and the other one's the output, and likewise here. And then it also has the 1/8 inch phone plug, stereo phone plug, input and output, and once again they're just wired together, so even though it may suggest input and output on the back panel, it doesn't really matter which one's which. Then there's also the electret microphone here and the power input. So you've got the line level inputs, buffering, amplifying, filtering, and then there's a circuit for the electret microphone. There's the power supply section. There's the mixer section. Then there's a mixer, amplifier, and active filter stage. Then there's the bandpass filter, which separates the audio signal into the 6 different bands. And then there's the Nixie tube driver circuit. And then down here is the circuit that generates the high voltage for the Nixie tubes, and also the Nixie automatic resetting circuit. So I'm going to go over each of those in turn and do a brief exploration of them. There are only really a few different types of integrated circuit used in this Nixielyzer. One is the 7808, which is a 3-terminal voltage regulator. Basically the same as the 7805, but it has a slightly higher output voltage. And by offsetting it from ground with the forward voltage drop of the LED, it raises the output even higher to 10 volts. So the LED that's used here has a roughly 2 volt forward voltage drop. And when you apply that to the ground input of the 7808, it makes it think that the ground is 2 volts lower, so it outputs 10 volts instead of 8 volts. That's a pretty normal trick. And you've got that, and you've got a couple of 555 timers, which is a classic. You have 3 National Semiconductor LM358, now made by Texas Instruments since National Semiconductor was absorbed by TI. This is also an industry standard part. It's 2 op amps per IC, so there's 3 ICs. And then you've got a couple of more specialized circuits. You have the bandpass circuit, which is the BA3830S, and then you have the dual compander expander analog stage IC, which is an NCY 9100. So I thought I would go over those ICs briefly. Here's the NCY 9100. It's by On Semiconductor, and On Semiconductor, by the way, is the name that was given to Motorola's semiconductor components group when it was spun off from the main Motorola. And they continue to make, I think, pretty much the whole line of Motorola's discrete, standard analog, and standard logic devices. So I just think of On and think Motorola. So this is a Compander. It's a versatile, low-cost, dual gain control circuit, and it doesn't mean there's a dual gain, it means it's a dual circuit. It's a gain stage with a control circuit, and either channel or either half of this IC can be used as a dynamic range compressor or dynamic range expander, and it can also be used due to its internal component sections. It's widely used in things like cell phones, audio circuits, dynamic filters, CD players, things like that. And it's really divided up into the one circuit, which has the pins on this side, and the other circuit, which has all its pins on this side. And then there's a common ground and VCC pin. But otherwise, all of the one circuit's pins are on this side of the chip, and all these others are on that side of the chip. It's really kind of hard to figure out initially how this thing works. So what I did is, after a little digging, I redrew it like this. So it has an op amp in it, and it has it's designed for single power supply, and I wrote down its major attributes. It's 2 duplicate channels. It has a full wave rectifier stage right here, which detects the average value of the so-called rect-in signal. That's the rect-in here. Whatever audio signal you put there, the output of it is the average amplitude value of that audio signal. So it's like a signal that goes up and down as the loudness or the volume of this audio signal goes up and down. Then there's a linearized temperature compensated variable gain circuit here. Think of it as another op amp. And it's got this delta G input, and it's variable gain, and its gain is controlled by the output of this. So the level of this analog signal controls the gain of this channel, and this is where you'd put your signal through it. And then you've got a resistor biasing circuit here, but it doesn't go to power supply. It goes to a so-called R3 input, which could be tied to anything you want, and the other side is tied to ground. And then this whole junction here is brought out to a pin called INV input, or inverting input, and that's what it is. It's the inverting input to the op amp. The non-inverting input is tied to a 1.8 volt internal reference, which is generated from the VCC power supply to the chip. And then you've got the output. And there's also 2 more pins. There's the rect cap, which is a capacitor that basically hangs on the output of the rectifier and helps stabilize it. You may or may not need that depending on how you're using the circuit. And then there's a total harmonic distortion trim point that's brought out here on the gain stage. Now, if you didn't want to use this, you could actually just, bring a signal right in here and take an output from here and just use the op amp, or you could make a more elaborate circuit by using this resistor, for example, tied back to here, and thereby get negative gain with a fixed gain resistor. You could do a lot of different things. The circuit is designed to run on a monopolar power supply. In other words, it doesn't need to be a plus and minus power supply, and it shouldn't be. it's designed for everything to be above ground. Once again, you can have an external filter capacitor at the rect cap. It's part of the rectifier averaging block. The size of the capacitor dictates the gain response time. So if you have a signal that's wildly changing its amplitude here, and you have a decent sized capacitor here, then the output of the rectifier will respond more slowly to changes in amplitude here. But if you have a smaller value capacitor, then the signal here will respond more quickly with the gain or the level of the signal here. The THD trim input provides a means of nulling internal offsets for low distortion operation. So again, that point may or may not be used. So this circuit is used in both of its halves, one half being the microphone input circuit and the other half being a buffer amplifier and active filter stage. Now, I didn't go into all the weeds on this, but I figured I'd just go over the basics of how it works. So let's start out with the microphone input. It's an electret microphone, which means it needs to be connected from a positive power supply through a resistor to its output pin, and then the other pin goes to ground. So it actually has internal electronics, and it gets its power from current flowing down here through the resistor, and then it modulates that and sends the signal out here. So there is a series capacitor here, which should remove any DC value of the audio signal coming from the microphone, and then it's biased to V mic, which is a lower level microphone power supply within the Nixielyzer circuit, and that is applied to the rectifier input. So this is able to track the volume on the microphone, and it feeds that into the gain stage, but the gain stage doesn't get its input from the microphone. Instead, the microphone signal goes over here and goes into the op amp, but it's mixed. This is a mixing junction here, so it's like an additional gain stage. So the output of the op amp comes back here. It's a series resistor and a capacitor to ground, which turns into a low pass feedback element, and then that signal's passed back around to the minus input, so you have a gain component there. And then the output is also fed back through this capacitor and back into the gain stage of the chip, and then brought back to the negative input. So it's a dual feedback, essentially. You've got this feedback here with this configuration, means it's a low pass feedback element, and then this configuration is a high pass feedback element. So essentially what you're doing is you're creating a band that this circuit will pass and excludes things that are higher or lower than that band. So it's really a band pass filter. And the output then is brought to a front panel potentiometer. This is the mic level adjust potentiometer. And then there's a mixer circuit, which brings in the output of the line level inputs. I didn't show that here because I'm just focusing on this one chip, but its output is also brought to a level adjusting potentiometer on the front panel. Then those two are mixed, so here's where you're mixing the microphone signal and the line level signals. And once again, a series capacitor to reject any DC component. And once again, we're not using this gain stage directly. We're bringing the audio signal in through this resistor to the minus input, but here's the interesting thing. The same signal is tied to the inverting input directly, which it looks to me like it's shorting that resistor out. So, you know, I didn't trace the circuit board files, but that's what's shown on the schematic in the manual. So it sure looks like it didn't really need to do this except to not have it floating in space. So it looks like we're directly feeding the audio signal into the inverting input of the op amp here. And then there's, again, the V mic signal, which is 5.6 volts. And that has a series resistor, and then comes down to both the gain input and the rectifier input. So it's a DC value here, essentially. But is it? Well, no, the output is coupled through it, which once again turns it into a high-pass feedback element. And I'm guessing this is a compander circuit. I didn't analyze the circuit that thoroughly, but it would probably turn out that that's causing this to become a compander. In other words, it reduces the dynamic level. And then you've once again got a low-pass feedback element here and the high-pass. So it's band passing again. And I think basically it's a band pass, a buffer, and a compander. That's my story, and I'm sticking to it unless I hear otherwise. And then once again, you've got a DC blocking AC passing capacitor, and then bias to ground, and then another RC network, and then it goes directly to the bar graph circuit. So that's the essence of the NCY9100 in this circuit, what it's doing there. So the other specialty IC in the Nixielyzer is the ROM, or is it ROM? I don't know. I always call it ROM. BA3830S. It's a 6+1 band bandpass filter for spectral analyzer displays with an internal recording indicator output. All of the capacitors comprising the filter are internal to the IC, making it possible to significantly reduce the number of attached components. It's commonly used for displays on, CD players and mini audio components and car stereos and so on. Obviously, with only 6 bands, it wouldn't be used for scientific analysis, but it's okay for a pretty display. And this is the internal diagram. You've got a reference current generator circuit, 2 of them actually. Then there's a line negative feedback pin for this internal op amp, a line input into the negative input. And then there's this circuit here. It's got something to do with a recording signal. I didn't look into that. Then you've got all your bandpass filters and your detectors going straight to your outputs. And then there's this one for recording level, which is a separate part of the circuit that isn't used here. So I would imagine we would find that this whole op amp is disabled and its output on pin 11 is probably not even used. This is similar in function in many ways to some of the National Semiconductor bar graph ICs, except it has fewer bands and it is designed not to act as a VU meter as those chips are intended, but as a spectrum analyzer type IC. So let's go down to the nitty-gritty here. So here's the line level inputs. Once again, the inputs and the outputs are just tied together, so it's just a pass-through for both left and right channels. And those are brought into mixing junctions through resistors, so the right RCA jack line level signal comes to this mixing junction, and through the same value resistor from the left terminal, which is the ring on the 1/8 inch stereo phone jack. So that signal, if it's brought in there, is mixed. So you could actually have 2 audio components in here feeding the Nixielyzer at the same time, and one of them could be brought in through the 1/8 inch stereo phone jack, and the other one could be brought in through the RCA jacks, and they could both be feeding at the same time, and their signals would just be mixed. The right channel here and left channel same wise here. Or you could just have one of them turned on and the other one turned off, and that would essentially give you 3 inputs. You'd have the mic input, you'd have whatever input comes into the RCAs, and whatever input comes into the phone jack. But you wouldn't be able to control the relative amplitudes of those. There's no separate balance control for those. But anyway, so you get this mixed signal here, again, right channel and left channel. Capacitor to block the DC component, and then it's a very straightforward filter circuit here. It's basically acting as a buffer, and it inverts the signal because the audio is being brought into the negative input, but that doesn't matter. The circuit doesn't care whether the image is upside down or not, because it's not giving you a waveform, it's just giving you an overall amplitude in each band. So here the left and right channels are mixed with the balance control in the front panel. And once again, AC coupled through a capacitor. And now here's your line level volume control on the front panel. And then let's go down here to the microphone circuit. We have our VCC, which is roughly 10 volts. You have a resistor and Zener diode voltage regulator, which gives you your 5.6 volt V mic power supply level. It has a filter capacitor, and it provides the V mic signal to, I draw these little lines, arrows that help me find where the signal is also used. It's used up here on the mixer amp, part of the NCY 9100. So this is the electret pull-up resistor here from the V mic power supply, and its output is capacitively coupled into the rect in of the NCY 9100. We already discussed the fine points of that earlier, so I'm just going to move right ahead to the output. The output comes through here, comes up here and goes to the mic level control potentiometer on the front panel. And that's mixed with whatever's coming from the line. And now we go into the other half of the NCY 9100. Already discussed how that works, so I won't repeat myself. You get your line level output. Already discussed the signal this far. And now it is applied to the internal op amp. And you can see here that for the record level indicator, it's just being disabled by tying a resistor between the 2 pins, so it's doing nothing. We're only using the line level input that's used to feed the bandpass filters. And here's your outputs, all 6 of them. And there's also a couple internal points that need to be brought out to ground with capacitors, and those are over here. But now we have 6 identical circuits. It's an RC network, and then this is going to be an amplitude modulated signal that's proportional to the level of that particular band coming out of the bandpass filter. And this juncture here can be pulled to VCC, which is 10 volts, and there's a local filter capacitor for that, and then it has a series resistor, and then in that step we had earlier where we're using the tweezers to short out 2 pins on the circuit board per band, that's essentially pulling each of these nodes hard up to VCC, which overrides any modulated signal coming out of here, and that's how come it's used for burning in the tubes. But that's what's going on there. Now you've got the op amp, and it's driving a transistor, and this transistor is working with the Nixie tube. You've got a high voltage power supply up there, let's say it's around 140 volts, and it's applied to one side of a Nixie tube. Then the other side goes through the resistor, or through the transistor, and then through a resistor and out. So you've got a current flow from the high voltage power supply to the Nixie, through the transistor, through the resistor, and down towards ground. the amount of the signal that's applied to the Nixie tube depends on the signal coming from the output of the op amp, and the output of the transistor is fed back, so it's a servo circuit. It always makes sure that whatever is actually done out here with the Nixie tube remains proportional to the signal coming from the bandpass filter. And we have that 6 times for the 6 Nixie tubes. Now let's jump over here to the power supply. I should have really done this first. There's a 220 microfarad filter cap coming off of the already regulated power supply. There's the power switch. There's a so-called VB, which is used twice here and here in the high voltage power supply. So this is the highest voltage available. And then you've got the 7808, which is putting out a 10 volt signal as VCC, and we've already discussed where that gets used. Then we have another Zener regulator supply here, which knocks the 10 volts from VCC down to 5.6, and this is the so-called VNF signal, which does not appear to be used by itself anywhere in the circuit. But then once again we have another filter stage here, a series resistor and a capacitor to ground, and that provides the, even though it's shown as a down arrow here, it's not a negative voltage, it's still a positive voltage. I just repeated the symbol used in the original schematic, and that's used twice. It's just, again, I have these arrows pointing generally where they go. It's used here and it's used here. And that is because when you bring an AC signal into these op amps, the output is going to want to be based on that. If you have a single polarity power supply, in other words, it's some voltage and ground, you can't be bringing in negative signals here, so you have to bias the positive input of the op amp to roughly half of the power supply. And we already know that the output VCC is 10 volts. We're regulating it down to about 5.6 volts and filtering it, and then using that 5.6 volts as a virtual ground level for these two op amp stages. So that's what that's all about. Already discussed somewhere else how the VCC is also used to generate the 5.6 volt microphone power supply. So we've got the power supply taken care of there, and now we've got the high voltage generator circuit. We start out with a 555 timer IC configured as an astable multi-vibrator. So it's going to be putting out a square wave output signal. And you've got VB here, which is coming from over here. It's the highest available and basically not regulated locally power supply as a small value isolation resistor. Applies power to the IC. Negative side of the IC is at ground. Now this configuration here is right out of the application notes. It's a classic configuration for the astable multivibrator. You take a VCC or whatever it is and go to the discharge output, and then another resistor to the threshold input, and tie that directly to the trigger input. That's what that is. So the threshold and the trigger pins are tied together, and then from that point a capacitor to ground, and that causes the 555 to generate a square wave signal. Now, internal to the 555, in case you're not aware, there's a 2-node voltage divider inside that divides the positive power supply by 3. And so with a, whatever the voltage is here, say it's roughly 15 volts or 12 volts or something. Let's say it's 15 volts for convenience. The internal resistor divider in here is going to produce a 5-volt internal signal and a 10-volt internal signal, which are used for two internal comparators. And the CV pin here is connected to the juncture of one of those internal voltage divider points. So you can actually skew the internal voltage divider by overriding it with a signal here. And that causes the resistor values you've got here to essentially be, they don't change, of course, but it changes what effect they have on the output of the 555. So you can essentially steer the output of the 555 somewhat using this trim potentiometer here, which takes its top from the high voltage output of the circuit way back over here. So it's essentially like a feedback element. We're taking whatever voltage is being generated by the high voltage section, tapping off of it, passing it through a transistor, and that pulls down from this pull-up resistor, and that is used to provide a steering voltage back into the internal comparator circuit, and that makes for a stable oscillator that you can tweak with this trim pot. And the end result of that is you can adjust what the high voltage is, and then it will regulate it to that even when other things change because of this feedback we have here. So that's what's going on there. Now the output of the 555 is run into a MOSFET here, and this is a power switching element. And then you've got your VB again, that's your unregulated, at least locally, high voltage power supply of roughly 12 to 15 volts. It has a filter capacitor here, 560 microfarads. It goes through this inductor, and then it has some local filtering here, and then it runs down into the MOSFET, and then from there to ground. So the square wave coming out of here is going on and off at a fairly fast rate, and it's constantly charging the magnetic field in the inductor and then allowing it to collapse, and then charging it, building up a new electrical field, letting it collapse, doing that over and over many times a second. And every time this opens up, the energy in the magnetic field here has to go somewhere, and what it does is it collapses and generates a high voltage at this point, and that's capacitively coupled and then applied to this circuit here, which I think acts sort of like a voltage doubler. At any rate, it rectifies what you've got there and filters it, and you end up with your high voltage output. So this is again a fairly classic switching power supply type of step up voltage circuit. And there's one other part to the circuit, also using the VB line, since it's associated with the higher voltages as a power supply, comes over. It's another astable multivibrator using the other 555 timer IC. Once again, the configuration is almost identical. There is a resistor from the VCC pin of the chip to the discharge output, then another series resistor comprised of two fixed resistors and a trim potentiometer going to both the threshold and the trigger pins, and then a capacitor to ground. So it's really the same configuration here, but apparently to get the right values it was necessary to double up two resistors in series. That would give a 2.6K resistor overall, and then 202 430 ohm resistors, so 860 ohms, and then a 1K pot. So once again, it's generating a square wave output, and the difference between these two, other than the frequencies are very different, is that this one's being used in a feedback loop and this one is not. So here, where the control voltage point on the IC is got this feedback element going to it, on here it's just stabilized with a capacitor to ground. So it's not being used in the same way, and the internal voltage divider is unmolested essentially. So you get a fairly low frequency square wave output from this, which is adjustable in its duty cycle, I believe. I think we're changing the duty cycle here, and probably the frequency as well. Anyway, that output is applied directly to another transistor, which is where all the current from the high voltage outputs needs to go through in order to get to ground. So if you turn this on, it's acting like a switch that's controlled by this 555. So whenever the output of this is on as part of its square wave signal, then this transistor turns on, and there's a path, and all these neon Nixie bulbs are operational. And then when the square wave output is off, the transistor is off, it's not conducting, and that means there's no current flow for any of these, and the Nixie tube's essentially off. So essentially the Nixie tubes are being pulsed on and off at a rate that's too fast for you to see it with the human eye. And why is that done? It's because there's a characteristic of these particular IN9 Nixie tubes that under certain conditions they can kind of get soured, and instead of the discharge beginning at the bottom of the tube and progressing upwards, as you would expect, it may choose to start at some intermediate point on the tube and then build up from that point. So it may start in the middle of the tube and go up, or 1/3 or whatever. I don't know exactly what's going on with that, and it isn't explained in the manual, but my guess would be that the tube is arcing over or something, or able to conduct without causing the orange glow until it gets to a higher voltage level of the tube, and then goes from there. But by turning power on and off many times a second, it apparently breaks its tendency to do that, or it prevents it from doing that in the first place. So that's what's going on there. So I think that's all I want to go into with the schematic.